Hello, my name is Luke and welcome to this PyTorch tutorial series. In this video, we're going to look at model interpretability or explainable models. How we can try and understand what or how our trained neural network model is doing what it's doing. What is it actually using from the input in order to make its decisions? As per usual, all of the code is available in my PyTorch tutorial GitHub repo, a link in the description, and remember to subscribe to follow along for more content. So as I mentioned, we're looking at how to understand the decisions our model is making. The method we're going to be using is called LIME, or Local Interpretable Model-agnostic Explanations. But before we get into how it works, let's look at a bit of a motivation to why we might want to understand or have some explanation for what our model is doing once we've trained it. So we've already looked at the training process for our neural networks. Now let's look into what we can do to try and better understand if our model is behaving as expected. The example I've got here is we have some classifier, maybe a convolutional neural network classifier that is trying to predict whether or not the input image is of a wolf or a husky. And you can say that, see that here we have our model and it is able to 100% or roughly 100% accurately predict whether or not the image is a wolf or a husky. You can see here, though, that we've got an incorrect prediction. So this might be one thing you want to use LIME or something similar for, understanding why your model may have gotten a prediction incorrect. So you can see here that this husky was predicted as a wolf, and we might want to understand why and why it got, or why it made the decision for the other models, or for the other images as well. So the question is, can we reliably employ this model, right, and deploy it to some application? So using LIME, again, without going into it just yet, let's have a look at what our model is looking at in these images to make its decision. So you can see the grayed out area is regions where the model is not interested. And here we're just showing the areas of the input image that the model is interested or using to make its decision. And you can see that for our wolf pictures, it is really focusing on the snow in the background. And for a husky, it's more looking at the actual dog itself or the grass in the background. And you can see for this incorrect prediction here, we have a husky in the snow, and it's looking at the snow, and it's using the snow to determine whether or not the actual image is of a wolf or a husky. So even though it might have gotten a really high accuracy, 90+%, there's a bias in our data such that pictures of wolves that we have are mostly in snow. So we've got an over-representation of wolves in snow. And so our model's just like, oh, I can just look at the snow in the background, and that's good enough to accurately predict whether or not the image contains a wolf or a husky, or should have the label wolf or husky. But of course, that simple model is going to fail in cases where we have a husky in the snow. So even though your model might be performing really well, or maybe it's performing really well in your training and your testing with the data set you have, but once you deploy, it started to perform really poorly. Using the step before deploying your model to try and make sure the model is doing what you'd expect can be very important, because our neural network models aren't magic, whereas, kind of treat them a bit like a black box. They are using some part of the input image to inform its decision, and working out exactly what that is, making sure it reasonably looks correct, can help us be more confident that our model is doing what we'd expect. So let's have a look at LIME. So with our complicated models, like our neural networks, which is what we're going to use, though, as you might tell from the name, LIME is model agnostic, so you don't need to just use neural networks. You can really use any system, but we're going to focus on neural networks and convolutional neural networks as our model. Neural networks are nonlinear models, very complicated, and it can be very difficult to work out what parts of our input image or input data our model is using to inform its output. But what LIME does is it utilizes the fact that a simple linear model, while not very expressive and not very, I can't really model very complicated nonlinear functions, it is very explainable or understandable just by looking at the parameters within that network, within that single layer. So If we consider a perceptron, so it's a single linear layer, and we have our input feature of one input parameter per input feature, so that's what our linear layer is. And let's say we have a simple single output, yes or no. So we have one parameter per input. Maybe it'll be useful if I sort of draw this out a little bit. So I have my single perceptron and a single output, and we have a weight is represented by these lines per input. That's my weights, my input, and that's my output. So one parameter per input that go into our, well, that's summed, and that's our output there. Okay, so another assumption that we're going to make here that helps with the explainability or the interpretability is to make sure that our input features are all normalized. We've already talked a little bit about why training with normalized features is important. If the magnitude of one of our features is very large in comparison to other features, then that can sort of overwhelm or dominate our network. And our model might try and compensate by shrinking the parameter, or the corresponding parameter, but it's just much better to actually make sure that our inputs are normalized. Let's assume that our inputs are all normalized or standardized, maybe between 0 and 1. If we train this network, and as my example shows in the notebook, one of the weights for one of my inputs is, like 1,000 or 100,000, and then one of the weights for the other inputs is like 10, well then, obviously this input here is going to contribute a lot more to the output than this one. Well, our model has learned that this first feature here is really important, so it scales that a lot, scales that up. It could also be negative in magnitude, so if it was like a negative 1,000, we're looking at the magnitude here. So this input here is really important for the positive case, so when we want to make the output really large, and this input here is really important for the negative case, so for the false case, because that'll make the output really negative. So by looking at the magnitude, we can know how important those input features are. And by looking at the sign, we can tell which way it's going to swing our output. So really interpretable just by looking at the magnitude of the features. That's basically what we say in this text. Of course, we want to use our deep neural networks or convolutional neural networks. We can't just use a linear model. So what do we do? Or what does LIME do? So what LIME does is we have our trained model, our trained neural network, and we basically try to fit a small linear model for a single data point of our data set, the one we're trying to interpret. What we do is we pick a single data point from our data set that we want to understand, so maybe this one here. And what we do is we pass that through our neural network, we get our probabilities on our output, and we try and train a model to a linear model to replicate the output of our neural network, right? And we don't just do that for the one input. What we do is we take that input and we perturb it in some way. So we're going to look at tabular data first, but with images, you might block out certain regions, which is what we do with images, as we'll see. We might sort of block out certain regions of the image. We pass that through our trained neural network. We see the outputs. And what LIME does is it trains a single linear layer to try and replicate the behavior of our complicated neural network on this perturbed data. So it's the same data point, the one we're trying to explain or understand, but we perturb it in some way. So that's why it's called local interpretable model-agnostic explanation, so local interpretable. So here's a sort of a diagram from the paper that I used to explain. This big cross here is our true data point, and we perturb it a lot. We get all these other data points here, and basically we try and fit a decision boundary that replicates our neural network, say. So we try and fit a linear model to say, when does it switch over from classifying one to the other, and we try and fit a single linear layer that replicates the behavior of the model for that one perturbed mini set of data that we've constructed artificially. Once we've done that, then we have that linear model, and then we can, by looking at the parameters of that linear model, see what parts of the input are important just by looking at the parameters. And because it's sort of locally true or locally reflects the behavior of that neural network, we can also say that, for this linear model, if these features are important, then that's also true for this neural network, at least for this particular image. So this particular image, we know what perturbations that we make to our model affect the output by looking at the parameters of that single linear layer that we train for Lime. So for Lime, we train an actual linear layer for every single example we want to understand. Right. So we're going to look at tabular data here, so some numerical data, in which case the perturbations are just sort of adding random noise to our data to try and perturb it a bit and seeing how our classifier sort of switches from classifying on its output, or changes the probabilities really. So luckily for us, Lime, which you can look at the paper if you want, about 2016. I'm not sure if it was actually published earlier than that. Why Should I Trust You is the paper where they introduce Lime. And you can go into that if you want some more details, case for explanations, similar to what I've said before. Right. So you can just pip install Lime and use it in Python. And that's what we're going to go through for the rest of this video. So we're going to look at the tabular case, and we're also going to look at how you can use Lime for images as well. It covers the sort of two main use cases that we've seen already in this series. So generate data by perturbing, switching on and off the features, and calculate. So adding noise or just turning on and off the features, basically zeroing the features. Okay. So it also has ones for text data as well, if you want to use that. So we're going to use this Wisconsin breast cancer dataset. So basically we have a whole bunch of features for breast cancers, and we want to determine whether or not they're malignant or benign, right? Classify whether or not we should be concerned. So this dataset, you can download in a number of ways. The CSV comes in this, got the CSV actually in the repo, so you can just use it from that. So we've got 30 features in this data set, and the first thing we need to do is train a neural network model in order to classify this data, and then we're going to use that with Lime to try and understand how it made the decisions that it made. So it's very similar to classifications we've done before with our multi-layer perceptron, so I'm just going to use a multi-layer perceptron. I've constructed my data set here, PyTorch data set, by just loading up that CSV with pandas. You can go into that if you want to try and understand what's going on, but we basically have 30 features and also a column where we have the diagnosis for malignant or benign, and we're just mapping that to 1 or 0. And importantly, we are normalizing all the features. So every feature, we're subtracting the mean across the data set for that feature, divided by the standard deviations. So every particular feature has mean 0, standard deviation 1, because it's important in this case, because if you have a look at the actual data set, you can see that some of the features here are quite large, in the hundreds, and you can see some are very, very small. So it's important that we standardize these, not just for training the neural network, but also for when we use Lime. Okay, so just a very simple MLP, 30 inputs. We're going to have 2 outputs. We're going to use a cross-entropy loss to classify this. So this is not going to take very long at all to train. So we'll just do that now. See, very small model, very simple data on a GPU. It doesn't take too long. So you can see we get a 99.34 training accuracy and a 96.46 validation, which is pretty much what I get every time. And we can have a look at the plots. Okay, so very simple. I've covered those sorts of things a lot before, so I won't go into that anymore. But now that we've got this, 96% or 96.5% validation accuracy classifier for this breast cancer data, you might just say, okay, well, now we can classify breast cancer, but maybe we need to make sure that it's actually usable. Or if you were to give this to a doctor, they don't want to just see, oh, it said you have malignant cancer. Oh, I guess that's the diagnosis. Then no, they will never want to trust that. But maybe if you say, hey, the model has paying attention to or is interested in these particular aspects of the cancer, what do you think? And that's why it's concerned. That's a bit more of an information or informing the doctor as to rather than just providing a diagnosis, which they might find more useful. So to use the Lime package, we need to define a few things. The first thing we need to define is a function that we're going to use later and pass to our Lime object that basically takes in a NumPy array or a batch of inputs as a NumPy. Remember, Lime works with any sort of model, any sort of technique, not necessarily specifically PyTorch. So you basically need to define a function for your specific use case. That is basically the forward pass of our model in this case, but depending on your method, it could be something else. So in our function, we're going to take in that NumPy array. It's going to be a batched array similar to what we've seen before for multi-layer perceptrons. We're going to make sure our network is in evaluation mode. Cast that NumPy array as a float tensor, put that on our device, do our forward pass, get our logits, and turn those into softmax. So Lime is expecting the probabilities for our classes. So we'll softmax over the output, put that on our CPU detach, and return it as a NumPy array. Again, Lime needs that as a NumPy array. Again, a batch of outputs. So we're going to define our class names. Class 0 is benign, malignant is 1. And we're going to give Lime a whole bunch of training data and labels as well. Lime can, though we're not really doing it here, actually try and determine what parts of the training data are important for certain classifications. So it can do like a little check at the start or a classification to determine what features of your data set are actually important in the tabular case, and then sort of focus on those, if that makes sense. So you need to give it some data. If you need to give it some data anyway, though in our case we're just going to use we're going to tell it to use all the features, so it doesn't really matter. But later on here you can specify to use less features. So I'm going to convert the torch data in my dataset class to NumPy arrays. Same with the labels. That's just what I'm doing there, and also the feature names, which is just the headings of the my pandas array, pandas data frame. And it's just going to use that for display later on. So we're going to pass it all into my Lime tabular explainer, the training data, the mode, so you can do regression, I think, as well. We're going to do classification. This is what our model is doing, classification. So the names of the classes and the names of the features. This is just false by default. You don't need to worry about that. We won't go into that part there. So we've created our explainer, and now it's time to give it a sample to explain. So what I'm going to do here is I'm just going to randomly select one of the training examples from my NumPy array, and I'm just adding on a batch dimension at the start for my NumPy array. And then we just do explainer.explain instance. We give it the instance from our dataset that we want to explain. We also pass it the function that does our forward pass of the model, or whatever process you want, and also the number of features you want it to sort of test. And I'm just using length feature name, so basically all 30 features. And then we're going to get the prediction, and then the actual prediction from our model and the actual. And then finally, we're going to show in notebook, which gives us a nice little graphical result. So we've performed the explanation, happened very quickly. It doesn't take too long, just training that little linear layer. And you can see the prediction was malignant. The actual was malignant as well. That's from my MLP predictor function we had. And we can see that the probability was 100%. The model's very confident. So the interesting part is these two tables or columns here. So start in the center, I guess. So we have two sort of columns, benign and malignant. And what we have here are the feature names that kind of cut off here. So the features basically ranked in order of importance or how they influenced the output. So you can say for this particular example, again, for this particular example, perimeter worst was the highest or most influential, and this radius SE, radius worst, etc., etc. And these top three were actually just as contributing to the output. So these numbers here basically tell you how much did this particular feature influence the output for malignant. So all these outputs here for malignant, you can see they scale. The explanation for Lyme is basically that these tell you how much that it contributed to this 100% prediction probability. So if you were to remove perimeter worse, it would be 0.21 or 21%-ish less confident that it was malignant. And the same is for benign. These tell you sort of contributions for benign. But you can see benign here is 0, so it doesn't really correlate exactly to the probability prediction, but you can see which inputs or which features are skewing the model towards predicting malignant and which ones are skewing it towards predicting benign. And we also have like a threshold here that the model is, at which point the model is being influenced by. So the fact that the radius SE was greater than 0.27 is influencing the fact that is influencing the model to predict malignant. And then finally, this table on the far right is basically just has each of those features in order, similar to the center here, of influence, and also has the actual value of the feature. So perimeter worst was 2.30, radius SE was 2.49, and the colors just tell you which way was it skewing the model. So from that, you could inform your doctor that, hey, have a look at these features or these aspects of the cancer because they are leaning towards it being malignant. So we can also, as I said, only look at, say, the top 5. So it'll only use the top 5 to make its prediction. See, it actually took a little bit longer that time to try and work out the top 5 first. You can see that for this example, these features were predominantly skewing the model towards it being malignant. Or you can just use all of them like I was doing before. Okay, so you can have a look at some other examples. Let's have a look at, try and find a benign one. Here we go, benign 0.98 probability. And you can have a look at the features that skewed it that way. So there we go. Hopefully that makes sense, and see a very simple real algorithm to determine just by fitting this simple linear layer and perturbing the features of your input and just trying to replicate the behavior. You're just trying to replicate the behavior of your, complicated neural network or whatever with the simple linear layer. And note that it's model agnostic. So you can put whatever you want in this function, right, that you're using basically to generate the training data for your linear layer. It could be anything, right? So it's really model agnostic, and it's quite a simple but very powerful way of trying to understand what your model is looking at for a particular instance. So that takes us to line 4 images, where we basically do a very similar thing, except the way we perturb our inputs is a bit different. So just dropping out single pixels of our image is not very useful because you can still really tell quite easily if you're dropping like 20% of the pixels, you can still tell what the actual image is. So what Lyme uses instead is what are called superpixels, which is basically a method of segmenting up your image very coarsely. So a very coarse, rough way of segmenting your image. So you can see here, you can define sort of granularity of the segmentation. So we've got 3 examples here: very fine, coarse, and then very coarse. And high level, it just does that by finding and spreading out and finding regions of the image that have similar pixel values. So that's called a superpixel. It's used in a lot of different algorithms as well. And what we do for Lyme with images is basically, instead of dropping out a single pixel, we drop out superpixels. So we drop out large chunks of the image, and that way that has more of an impact on the actual features of the input image, right? We're dropping out large sections of the image, and then that'll sort of inform more of an impact on the output of our model, whether or not you want to use large or sort of coarse or fine superpixels. Really sort of depends. There's a trade-off. If you're using too fine a superpixel, then you're not really removing too much information from the image, and your model might not really change its behavior. But if you're using really large superpixels, then you have less of a fine-grained idea of what specifically in the image is actually your model is looking at, because it's dropping out quite a large area. You don't know within that super pixel, is there anything more specific? So bit of a trade-off, but more or less it's still useful. Okay, so we're not going to actually train a model. In this example, we're going to take a pre-trained ResNet that we've already seen before, so trained on ImageNet, and we're going to use that in this example. So here's just a few utility functions, converting the pill image to a torch image. That's just basically using our torch transforms to make sure we are converting our image into the form that our pre-trained network was trained off of. So rescaling 256 by 256, center cropping 224 by 224. That's just what the actual documentation says was used to pre-train the network, and these were the statistics for normalizing the image. And then pill to transform is just transforming the image to a pill image without the normalization, which we use for display. And we need to also, of course, define that prediction function, so that function that Lime uses to get the probabilities for a given input. Again, we have our image. We need to do our normalization and process as well. So here we're assuming that the image has already been cropped and rescaled. We are going to stack that because we want to put multiple images in. Lime is going to give us a stack of images, like a list of images, and so we just need to stack those as a single batch of images that we do our forward pass with our network. Again, softmax to get our probabilities and pass out that batch of probabilities as a NumPy array. Okay, so we're going to use this image of a kitten and a puppy for our example. So here is a classic example. We've trained a single class classifier, or multiple classes, but we only predict one class at a time. This image contains two possible classes, kitten and a puppy. What does our model predict it as? We'll do our forward pass. We can see the top 5 probabilities here. So Labrador, Golden Retriever, Kuzvats, Great Pyrenees, and Irish Wolfhound. So it's very much skewing towards the dog, and probably because the dog dominates the image a bit, and maybe because we're cropping it, we might be cropping out the cat a little bit here. But let's have a look at what exactly our model is looking at by using Lime. So we've got our Lime explainer here. We don't really need to pass it any parameters, unlike our tabular one where we had to pass it a few parameters. This is already really set up with the defaults, and we can just explain with our instance. Again, we pass the image, we convert it to do with the cropping and everything and make sure it's a NumPy array. We pass it our predict function. We say we want the top 2 labels. So what we're saying here is for this image and its classifications, look at the top 2 classes that it thinks it is, and perform Lime, the classification on those top 2. So I have like 2 Lime models here. Hide color, no. Number of samples. So this is the number of permutations of that image we're going to use to train our Lime model. So how many different superpixels we're going to drop out, how many times we're going to perturb the image. And as you can see here, we have to perturb and then pass it through our model to get the features and whatnot. So I'll just pause now and get back when this is done. So that's finished now, and we'll have a look at our results. Right, so Lime can display what is called the positive and negative masks. So basically regions of the input image that, again, skewed it towards being a positive output for that particular class, or towards negative or for that particular class. So which parts of the input image skewed the model towards saying yes, or which ones skewed it towards saying no for this particular class. Okay, so we're looking at the top label here, and we've got our original image, a positive mask and a negative mask. So these are the top 5 superpixels. So there's not just one superpixel, it's the top 5 superpixels that skewed our model, our neural network, towards it being classified as the top class, which is a Labrador Retriever. And then we also have the ones that skewed it towards being not that. So which ones pushed it away from that? And nicely for us, you can see that, yes, the dog was the thing that it was looking for when making the positive classification as the Labrador, and the cat, or the parts of the cat image that were mostly the cat, were the ones that skewed our model away from classifying it as the dog. Okay, so hopefully that makes sense. So let's try another image and look at a bit more of a complicated case. Okay, so here we have a hamper full of fruit. Now, our ImageNet classifier can classify each of these, a lot of these fruits individually, but now I've got an image with a whole bunch of them in it. So you can see the top classification was for a hamper, shopping basket. That makes sense. And then, of course, there's a lemon, there's a banana, there is a pineapple. So what's our model going to do? Well, it picked hamper, though I guess the overall image is of a hamper. So that makes sense. So now let's actually see for each of these top 5, what part of the image is it looking at? So we'll do a similar thing again. Top 5 labels, 1,000 examples, and we'll let that run and get back when it's done. All right, so that's finished, and let's have a look. All right, so the first one we're looking at is for label 0, so the top label hamper. So we can have a look at the positive and negative masks. So you can see that how many features? Top 3. So we're looking at the top 3 for positive, and we're looking at the negative. For the negative, we're looking at the top 10 for negative. So we can see that it's looking at the basket mainly for hamper, and you can see the banana here, and sort of black plain background for some reason is contributing to the negative, but you can see the fruit in the basket is skewing it away from being positive for hamper. We can also look at what's the next one, shopping basket, just by changing this label. Again, mostly looking at the basket for a positive, and the fruit again for negative. Let's have a look at something more interesting. Lemon. Okay, so let's have a look, see if it is looking at the lemon for lemon. You can see it does contain lemon in the positive mask there, so that's good to know. We can change the number of features to just the first one. Interestingly, the top one seems to be for the grapes. Top 2, the lemon is in there. So I wonder if, I don't know, in the training data for lemons, there's a lot of grapes. I don't know. But at least the lemon is in the top 2. And then the orange is also in there as well. So there we go. Banana, the next one. You can see the banana is in the top 3 as well. I wonder if it does any better with the top 1. There you go. The banana is in the most important part of superpixel of the image. So it is definitely looking at the banana when determining if there was a banana, or that part of the image is, informing the output of our classifier that, determines the banana class, right? So that's what's influencing the banana output of our model. 3. And the last one was pineapple. Ooh, pineapple. You can see the pineapple is in the positive mask. See if it's the top one. No, banana again. So I wonder if a lot of fruits are often together. You can see it's in the top 2. Again, this might just be an artifact of lime, but you can see it is in the top 2. So it is one of the most important parts of the image for informing the model whether or not it's a pineapple. So we didn't really look at the negative prompts, but you can see the negative ones are kind of a bit random. So for pineapple, it's looking at some of the other fruits in the input. We could also reduce the size of the superpixels as well, but if we reduce the size, it takes even longer to train because we need to train with more samples because we're perturbing smaller and smaller parts. But hopefully you get an idea here of what we can do with Lime and how it might be useful. So you might have a CNN classifier that is, again, might be medical images that's saying that, hey, yes, this image of cancer again maybe is a problem. Okay, well, that's great. It's a big image. What particular part of it is sort of making you say that? Well, you can use something like Lime to pinpoint specific regions of the image that are important. So not just for validating whether or not your model is doing what you want it to do, like we talked about way up here with our Husky Wolf classification, but also providing extra feedback or not just using your CNN model as a tool for predicting or diagnosis, but actually transforming it into a tool for explanation and detection. So, just like that, we've actually got like a banana detector, right, or a fruit detector from our model that was not trained to do that. So, very simple technique, but very powerful in the number of ways that it can help you. Like I said, have a look through the paper. It doesn't go into too much. It's not too complicated. I think it's, again, pretty approachable. If you want to have more idea of where you might want to use it and some other variations of it, download it yourself and have a go at this example. So I encourage you to play around with this. Again, the code is all available for you. If you liked that and it was helpful for you, make sure you like and subscribe for more. And let me know if you have any other questions or you want to see any other videos in the future. But for now, that's about it. And thanks for watching.